Hello, welcome to the eighth lecture for the Mathematics 11, uh, class 11, chapter 4, complex numbers and quadratic equations. So, till the last class, we have finished the algebraic operations, and we also saw how we can find the modulus of a complex number as well as the conjugate of a modulus number. Okay, so if to just to refresh, your modulus. Yes. So modulus of a complex number z. Okay. So if your z is equals to a plus I b. So modulus of z can be represented as mod of z, and that would be under square root a square plus b square. Okay. So this is your modulus. So essentially, we only find the sort of the the magnitude, or we only consider the real coefficients of both the real parts and the imaginary parts to get the modulus of a complex number. And we have also seen with the conjugate, what is the conjugate of a complex number z. So that can be represented as a bar on top of the complex number z, and that will be the where the sign of the imaginary part changes only. Okay, so these are the two things that we have seen. We did see how some of the relations can be formed, and we tried to prove a few, and we also solved a few examples to see how they are valid. Okay, so now we will continue with some examples which will use where you have to find the conjugate of an expression, where we will first use some part of the algebraic operands, and then we will find maybe the conjugate or the modulus. Okay, so suppose the expression that you are given is 2 6 plus 6i plus I 6 plus 6i. Okay, so this is the expression. You can say z is equals to this. Find both the modulus of the expression. Okay, so let's not call this z per se. Okay, so find the z. Okay, so your entire this expression. Okay, so z is this, and your conjugate of z. Okay, so we'll find both. So over here, since you can see that z is, we have to simplify to get the result of z, okay, to solve for z. So since you can see that this term is common, okay, so let's get that to one side. Okay, and you have 2 plus 5. Okay, so let's expand this. So you have it's 12 plus 12i. Okay, and then you have plus 12i. You have 6i plus 6i squared. Okay, then since we know that I square is equals to -1, so this will be 12, and this becomes -6. Okay, and then this will become plus 18 pi. Okay, so then what we are left with is 6 plus 89. And if you further simplify it, if you take 6 outside, 1 plus 3i. Okay, so this is your z. Now, when we want to find the modulus of z. Okay, so the modulus of z, over here, you can see that we have taken 6 outside. Okay, so we have taken 6 outside. So either you find the modulus of this or this. When we are finding the modulus of this, okay, so what you can do is since we know that the modulus is under root a squared plus b squared. Okay, so we know this. Now over here, since either put the coefficient inside the bracket and you find this, you take this as A and B. But if suppose you have a coefficient that you have taken outside, you don't consider this for your modulus calculation. For modulus calculation, you can just take this. Okay, so that would be actually you keep the 6 outside. Okay, you don't consider 6 inside the under root. Okay, you can take 6 outside, because even if you take it, it would be, you have to square the 6 also. Okay, if you take it inside, and if you take it outside, you are remaining with 6. So if you keep 6 outside and then you square the A and the B term, so you have 1 squared plus 3 squared, so you get 6 root of 1 plus 9, and that is 6 root 10. Okay, so this is your modulus of Z. Now conjugate. Okay, so conjugate, as we know that we have to change the sign. Okay, so it's the opposite sign to whatever your original complex number is. So conjugate of Z will be 6, 1 plus 3i conjugate of this. And since over here only only the sign of this actually matters, so you can have 6, 1 minus 3i. Okay, so this is your final answer. So when you have to find your mod as well as your conjugate, so when you're just given sort of an expression. Okay, let's take another. So over there, mostly we were using, multiplication between two complex numbers. We saw. Now let's see another example. So suppose you are given z is equals to 2 minus I and 1 plus 2I on 1 plus 3I 1 minus I. Okay, so let's see if we are given a question in this form, and we want to find find the conjugate of z. So first, let's solve for z to get z in a simpler form of a plus ib. Okay, so we want to get in this form. So z is equals to, so we will solve. So this is 2 minus I plus 4i minus 2i squared upon, you have 1 plus 3i, you have minus I and minus 3i squared. Okay, so since we know I squared is equals to minus 1, so this actually becomes plus 2. So 2 plus 2, you have 4, and you have plus 3i upon, over here you again, since I squared is equals to minus 1, so this becomes plus 3. So 3 plus 1, 4, and this becomes plus 2i. Okay, and now over here we've got it in the form of, say kind of like z1 upon z2. Okay, so as we have seen that while if you have division, okay, you can actually get it as z1 multiplied by the multiplicative inverse of the denominator. Okay, so to find z2 inverse, we need to find the conjugate of z2. Okay, it's the conjugate of z2 and the square of the modulus of z2. Okay, so let's keep this over here, and we will find the mod of the denominator. So we have, so let's find the modulus of, sorry, this would be 2i. Okay, modulus 2i modulus. So this would be Modulus would be 16 plus 4. Okay, 4 square plus 2 squared, and that is root 20. Okay, and conjugate of 4 plus 2i is 4 minus 2i. So you directly substitute for 4 plus 2i in the denominator. So you substitute your conjugate of the denominator upon the square of the modulus of the denominator. So you have 4 plus 3i multiplied by your conjugate. Oh, just wait a minute. Yes. So you have 4 minus 2i upon, we've already got the modulus. So square of this would be 20 itself. Expand your numerator again. So you have 16 plus 12i minus 8i minus 6i squared upon 20. Okay, so what you are left with now, since again I squared is equals to minus 1, this becomes plus 6. So 16 plus 6, you have 22, and this is plus 4i upon 20. So if you overall take out 2 from numerator as well as denominator, you are left with 11 plus 2i upon 10. Okay, so this is your z. Okay, so this is your z. Now to find sorry, not the modulus, you have to find the conjugate. Okay, so conjugate of z is actually 11 plus 2i by 10, conjugate of the whole, so 11 minus 2i by 10. If you further want to simplify it, you can also write it as 11 by 10 plus 1 by 5, because 2 by 10, so 1 by 5i. And similarly over here, this would then become minus 1 by 5i. Okay, so this is your result. Okay, so you can see that over here we have used both the modulus as well as the conjugate to first simplify for z to get z. Okay, and then we have found the conjugate of the number of the result of what we simplified for z. Now let's see another question. Okay, so okay, so the question is that z1 and z2 are complex numbers. Okay, and a, b are non-zero real numbers. Okay, numbers. What is the value of modulus a z1 minus b z2 the whole square plus b z1 plus a z2 the whole square? Okay, so we have to find the solution for this expression, keeping in mind that z1. Okay, so the question is if z1 and z2 are two complex numbers, okay, and a, b are non-zero real numbers, what would be the value of the expression where we have put a z1 minus b z2 under modulus and squared it, and similarly b z1 plus a z2 under modulus and squared it? Okay, so what would be the solution for this? Now, remember the property that we have is that z, when we were doing z inverse. Okay, so let's just write a simplified form of z inverse. Okay, so you have 1 upon z, that is z inverse, and we have seen that is equal to conjugate of z upon square of the modulus of z. Okay, so this is the property that we will be using for this sum. So now you have been given that a z1 minus b z2 the whole square, okay, plus b z1 plus a z2 the whole square. Okay, now you consider this entire bracket as your z. Okay, this entire bracket as one complex number. So in those terms, okay, so if you can see that if you change up the sides of the terms over here, you can get that square of the modulus of z is actually z into conjugate of z. So you can convert this into this form. Okay, so it would be easier for us to simplify it. So you can write this as a z1 minus b z2. Okay, now the modulus sign is not there. Okay, so we have taken out the modulus sign. Multiplied by a z1 minus b z2 the whole conjugate. Plus, similarly, for the second modulus term that we have over here, we can write it as b z1 plus a z2 and b z1 plus a z2 conjugate. Okay, now we will since this is conjugate over here, okay, and this entire conjugate, if like we had also seen that if you have z1 minus z2 the whole of conjugate, that actually becomes your a, sorry, not a, okay, so that becomes z1 conjugate of z1 minus conjugate of z2. Okay, so you can separate out the individual conjugates also. So if you again simplify it using this relation, you have z2 a z1 conjugate and b z2 conjugate, and similarly you have b z1 plus a z2, and you have b z1 conjugate plus a z2 conjugate. Okay, so we got this. Now you expand, okay, for the first two terms and then the next two terms. Okay, so then it becomes a squared, and then you have. So now over here again, if you multiply this, okay, a, and then you put your z1. Okay, so you have z1 dot. Okay, so actually it would be your squared again, and then you have your minus ab z2 z1 bar conjugate minus ab z2 conjugate into z1, then you have plus b squared z2 z1. Okay, so actually these would be in bracket, sorry, these would be in brackets. Yes. Okay, then you do the expansion for the second the bracketed the terms. So you have b squared, you have z1 conjugate plus uh, yes. So then you have your plus eb again. You have z2 z1 conjugate and plus ab z2 conjugate and z1, and plus a squared z2 z 2 conjugate. Okay. So now over here you can see that these terms can cancel. They cancel each other out. So what you are left with is a square. Now again z1 multiplied by conjugate of z1, you will get the square modulus of the complex number itself. So over here you can write this directly as z1 square. Okay, and then the next one you have b squared, and over here you have z2. Okay, so this is z2, the modulus of z2 squared, and then you have b squared, square of the modulus of z1 plus a squared. You have z2 squared, the modulus of z2 squared. Okay, so this is what we get. Okay, I'll just add one more slide here. Okay, so what we got was, let's just repeat it. Yeah, so you have a squared, z1 modulus squared, and then you have plus b squared, modulus of z2 squared, plus b squared, square of the mod of z1, plus a squared, square of modulus of z2. Okay, so first we try to take the z terms together. Okay, if we take, so z1 squared, if we take it together, you get a squared plus b squared. Okay, and then if you have plus, then you take modulus of z squared, z2 squared, and a squared plus b squared. Then what you get is a squared plus b squared. Okay, and you put these two terms together. Okay, as we have taken the entire a squared plus b squared as the common one. Okay, so what you get is z1 squared plus z2 squared. Okay, so this is what we get. So this is the final result or the final solution. Okay, so you can see that using the conjugate and using conjugates as well as modulus, you can find the different kind of solutions when you are given expressions, and you can also prove. Okay, so if you were given some sort of a expression and you had to prove it, so these come very handy when we are dealing with complex numbers. Okay, so we move on to the next part. So that is the Argand plane and polar representation. Okay, so for any point can be geometrically represented. Okay, in terms of your x and y axis. Okay, so we know. So suppose these are your mutually two perpendicular axes. So this is your x axis and this is your y axis. Okay, so you have your x axis and you have your y axis. And we know that this is your positive x-axis, this is your positive y-axis, this is negative, and this is again negative. Okay, so this is what we know. Suppose you have to, any point, okay, in this plane, okay, xy plane can be represented as a point. Okay, so suppose you have a point P. Okay, so the distance of point P from your x-axis and y-axis can easily be determined, and it can be written in this form. So point P, okay, is at a distance x, okay, and y, okay, from the two different axes. Okay, so this is also x, and this is your origin 0, 0. Okay, so usually O is your 0, 0. Now, as you can see that this x and y can be a pair of real numbers. Okay, so any point p, x and y, okay, and x comma y actually are real numbers. Okay, now since we have a complex number, okay, so you have z, which is actually, if you want to write it in terms of x and y also, you can still write it as x plus iy. Okay, so over here, x and y can be used to represent the complex number on this plane. Okay, and this plane that we have over here, this is called the Argand plane. Okay, when we are trying to represent your complex numbers. Okay, so the complex number z can be represented as pxy also. Okay, so pxy represents z, the complex number, okay, x plus iy on Argand plane. So over here, this Argand plane is similar to what you have in Cartesian system. Okay, so you have positive x, positive y, and differently. Okay, so this is what we do. So similarly, if you are given a point, okay, you can kind of, if a point is given on xy plane, you can write it in terms of complex numbers also. Okay, so let's kind of see and say some examples. Just okay. So let's take for example. Okay, so I will draw the axis over here. So you have the axis over here. So this is your x, this is your y, and this is positive. This is negative. This is again positive. This is negative. This is 0 or origin. So if you kind of have a scale on all your axes, okay, so 0, 1, 2, 3, 4, 5, say 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay, so suppose let's see first, we will have few complex numbers like say uh, 5 plus 2i. You have say kind of negative 3 plus I, and you have 4 plus 0i. Okay, and you have 0 minus 2i. Okay, so let's take z1, z2, z3, z4. Okay, and let's take z5 as minus 5 minus 3i. Okay, so let's take z1 for example, and let's see where we can plot it on the Argand plane. Okay, so 5 and 2. So over here, this actually corresponds to p, say 5 comma 2. Now both of these are positive, so it will be in the first quadrant. So since we have 1, 2, 3, 4, 5, 5 and 2, so this is where you will have your point p. Okay, so you can write it point P52. Okay, sorry, let's just change it. 5 comma 2. Okay, now the next one is minus 3 plus I. Okay, so you can write this as Q minus 3, 1. Okay, so now you have negative X and positive Y. So this comes into your second quadrant. So you have minus 3. So 1, 2, 3, minus 3 and 1. So this is your Q. This is minus 3 comma 1. Now you see for Z3, okay. Okay. So for your Z3, so you can see that when you have, a negative X and negative Y, okay, so over here we are writing it in terms of XY, where Z is equals to X plus IY. Okay, now the next one you have 4 plus 0i. So over here you can see that your y is actually 0. Okay, so this actually falls on your x-axis itself. So this is actually a purely real number. Okay, so this is a purely real number. So if you have 4 0, so this is your r, 4 comma 0. Similarly, when you have no real or no x value, but you have the y value, so this is 0 minus 2. Now this is called a purely imaginary number. Okay, imaginary number, imaginary point on the Argand plane. Okay, so over here, this will plot on the negative y-axis. Okay, so you have s 0 comma minus 2. And the last one over here, you can see t as minus 5 and minus 3. Okay, so when you have minus 5, minus 3, both of them are negative, so they are in the third quadrant over here. So you can have minus 5. So 1, 2, 3, 4, 5, and 3, 1, 2, 3, 4. It comes here. So this is minus 5, minus 3. Okay, so this is how you can represent complex numbers on the Argand plane. Okay, so this is the geometric representation. Suppose now you are just, given a point. Okay, so if I have a point here, okay, so this is x, and over here you can see this is 2, and this is 3. Okay, so suppose you are asked represent x 2 comma 3 in complex number form, in the form of a plus ib form. Okay, so you can write this as 2 plus 3i. Okay, so this is your complex number. So if you have a complex number, you can represent it geometrically on the Argand plane. And if there is a point on the Argand plane, you can represent it in terms of the complex number also. So this is where you have where you can use complex plane and complex plane or Argand plane. Okay. Suppose we have this point P. Okay, and we want to find the distance between the origin and the point P. Okay, so now the length, okay, OP, can be given in the form of root of x square plus y square, which then actually becomes the modulus of the complex number itself. Okay, so if you have the complex number over here, so we have 5 plus 2. Okay, so 5 plus 2, if you get the modulus or you x square or you get x square plus y square, the value of it, so you have 5 square plus 2 square, and that is 25 plus 4, and what you get is 29. Okay, so the length or the distance of point P from the origin O is actually the square, actually the modulus. Sorry, this is not square, this is the modulus of the complex number itself. Okay, so you can get it easily. You either, you write it in this form, or you, if you know the modulus of the complex number, that too will work. Now, if we take the conjugate of, Z1, so Z1 is 5 plus 2i. Okay, so the conjugate of Z1 will be 5 minus 2i. Okay, so when you have 5 minus 2i, so then your P1, suppose your point P1 then becomes 5 minus 2. So now since you have positive x but negative y, this actually comes in your fourth quadrant. So you have positive 5 and negative 2. So this is your P1. And if you, kind of join this together, the distance, okay, so the length OP will remain the same as OP1. Okay, length OP will be equal to length OP1. Okay, because it's, again, it's the modulus. We have seen that modulus of a number and modulus of its conjugate are actually equal. Okay, so you can then see that since they are equal, and these two, okay, 5 and minus 2, these 2 points P and P1 are actually mirror image of each other. Okay, so you can see that they are actually mirror image of each other. Mirror image of each other. Okay, so this is the entire concept of the Argand plane, and you have your the representation of complex numbers as points on the Argand plane. Now, one more thing that you have to remember, that x is actually always the real axis. Okay, and y is your imaginary axis. So all the coefficients that belong to the imaginary part of a complex number will always be plotted on the y-axis, and all the real parts or the real coefficients of the real parts itself will always be plotted on the x-axis. Okay, and as we have said that purely real numbers will be plotted on your real axis, and purely imaginary numbers will always be plotted on the imaginary axis. So this is the concept of the Argand plane. And next, we will see what is the magnitude and argument of a complex number. Okay, so we were talking about representing the complex numbers on the Argand plane or the complex plane. Okay, but we will see that there is another form of representing complex numbers. Okay, so before we move to that part, we need to know what is the magnitude and what is the argument of a complex number. Okay, so over here we can see that it's written that argument of a complex number is defined as the angle inclined from the real axis in the direction of the complex number represented on the complex plane. Okay, so it is either denoted by theta or your phi. So suppose this is your Argand plane. Okay, you have x and you have y. Obviously, this is positive. This is also positive, negative, negative. Okay. So suppose you are given the complex number 3 minus I. Okay. So you have 3 minus I. So you have positive, or let's take, kind of an easier example. Okay. So you have minus 3 plus I. Okay, so over here you can plot the point minus 3 comma 1. Okay, so minus 3 comma 1. So this you can see this will be plotted in the second quadrant. So if this is your 0, so you have minus 3, so 1, 2, 3, say suppose, and this is 1. So you have this point over here. Okay, so this is your P minus 3 comma 1. You draw a line. Okay, you draw a line, and this angle, okay, this angle measured from the positive x-axis, okay, so the positive real axis to the uh, complex number, okay, in the direction of the complex number is actually theta. Okay, so this is your theta, and theta can be given as tan inverse of y by x. Okay, this theta, this is actually the argument of z, or it is also written as arg in brackets z. Okay, so this is your argument. So then what is magnitude? Okay, so magnitude is actually again similar to how we were finding the length of the point from the origin. Okay, so it is also similar to the mod of the z. Magnitude is actually the modulus of z, so that is again x squared plus y squared, and that will give you, over here you will get that as minus 3 squared plus 1. So this is 9 plus 1 root 10. Okay, so root 10 is your magnitude of point P. Okay, and theta, so you can calculate tan inverse of, you have 1 upon minus 3. Okay, so you can get theta for tan inverse of 1 minus 3. So this is how you can represent complex numbers, okay, on an argon plane, and you can also, you have quantities or you have terms which are related to these representation. Okay, so this is actually kind of called the polar representation. Okay, so we will see there is another way where we actually use these terms, okay, where we have the theta and the magnitude actually coming into the picture and in for representation of the complex number. So we will try to do it in the next class. So for now we have only till we will finish it off here. In the next class, we will finish this polar representation part, and then we will solve a few examples where we will be using different kind of, the operations that we have learned with complex numbers. So, thank you.